Okay, so now that we have a basic idea of how covalent bonds form, how we can use electronegativities to describe those different types of covalent bonds, let's take a look now at how we draw these Lewis structures for more complicated things, things that may contain more than two atoms. So the steps that your book outlines are really good steps to follow for drawing Lewis structures. I will preface this by saying there are multiple ways to end up with the same Lewis structure. So if you look at other textbooks or you look online, you might see different strategies for coming up with Lewis structures. It doesn't really matter which strategy you use, as long as you end up with the same answer at the end. The way that your book goes through actually uh, is a good way because you're going to always end up with the right answer. And so that's the way that I recommend. The first thing that we want to do when we draw Lewis structures, because it's all based on the valence electrons. Lewis structures are based on Lewis dot symbols, which use valence electrons. Is to first of all count how many total valence electrons that we have. Okay, we can use the periodic table to determine that. There are a couple extra things that we need to consider. If the Lewis structure for the thing you're drawing has an overall negative charge, we're going to add electrons here to count. Add electrons for negative species. And if your species has a positive charge, you're going to take electrons away. You're going to remove electrons off of the species. And we'll see an example here in a second. Okay, so that's the first thing we want to do is count the total number of valence electrons. Then what we're going to do is we're going to orient or organize or lay out the atoms in a way that makes sense. We want to have sort of a skeletal arrangement of the atoms. What goes in the middle? That's the first thing, right? Define or decide what the central atom is, around which all the other atoms will be arranged. Generally, the least electronegative element is placed in the middle. Okay, the least electronegative is further to the left and down. That's is in the middle. And then we're just going to orient everything else around that central atom, and we're going to connect them with a single bond to begin with. Okay, and then we're going to make sure all the atoms are happy by giving them enough electrons to account for their octet. So let's take a look at an example. And we'll do the Lewis structure for the ClO3 minus ion. If you remember from your ionic nomenclature, this is the chlorate ion. We're going to count our valence electrons first. Okay, look at the formula. We have 1 chlorine, we have 3 oxygens. Okay, chlorine is in group 7, 1 times 7 is 7. Oxygens in group 6, we have 3 oxygens, 3 6 is 18. 18 plus 7 is 25. You will notice now that we have a negative charge on our ion. We're going to add that many electrons in because the negative charge tells us we have an extra electron here. Okay, so we add that extra electron in. If we had a -2 charge, we would add 2 more electrons. But in this case, it's just a negative electron. So we add that many electrons. So we now have a total of 26 valence electrons. This is important because when I draw my structure, I should have a total of 26 electrons in it. Okay, so I'm going to orient myself with the atoms. I have a Cl and I have 3 Os. Generally, if you have one of something in the formula, you stick that in the middle. Chlorine is also less electronegative, so that goes in the middle, which means if it's in the middle, the oxygens have to go around. Okay, we need to connect these things so they don't float away. We're going to connect them with a single bond to begin with. Okay, there's our basic layout. We're going to next start on the outer atoms, so the oxygens in other words, and we're going to give them enough electrons to make them happy. In other words, to give them their octet. The oxygen here on the left right now is sharing 2 electrons. Okay, so it actually belongs to the O as well as the Cl. So we need 6 more to complete its octet. So 2, 4, 6 plus the 2 that are being shared is 8. The oxygen on the right, you can imagine, is the same situation. It's sharing 2. It needs 6 more to complete its octet. Oxygen on the top, same thing. It's sharing 2. It needs 6 more electrons. Okay, so I take a step back and I look at my structure. How many total electrons do I have? Well, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I should have 26, which means I have 2 more electrons outstanding. Where am I going to put those electrons? Only place to put those remaining 2 are going to be on the chlorine, right? The oxygens don't have room around them. They're already full, happy with 8. So I have my 2 electrons that are going to go on that central Cl. Okay, I've accounted for all of my 26 electrons. Everything has their octet. So that's my Lewis structure. A couple of things to consider. This entire thing has charge to begin with. So I need to show that charge in my structure. Usually what you also do is if your structure is a polyatomic ion, you usually put it in square brackets. And then you have the charge on the outside. Okay. So that's your Lewis structure for ClO3 minus the chlorate ion. All right, let's take a look at another example. Let's say I wanted to draw the Lewis structure for HCN, hydrogen cyanide. We're going to follow the same steps, right? So the first step is to count the number of valence electrons. Look at the formula and the subscripts. I have 1 hydrogen, I have 1 carbon, I have one nitrogen. Hydrogen in group 1, carbon in group 4, nitrogen in group 5. Add those together, 5 plus 4 plus 1 gives me a total of 10 valence electrons. Okay, so my structure should have a total of 10. Now I need to figure out how these atoms are going to be arranged. Well, we said we're going to put the least electronegative element in the middle. Well, hydrogen is the least electronegative, but hydrogen cannot be in the middle. Okay, this is important. Hydrogen cannot be in the center because hydrogen can only form 1 bond. It is an important exception to the octet rule. In that it only needs 2 electrons to be happy. Or to fill its valence shell. Okay, so it's still following the whole keeping the valence shell filled thing to become more stable. In this case, the valence shell is the first shell, which can only accommodate 2 electrons. So if the H can't be in the middle, well, then the next electronegative element is C. And as a general rule, carbon, if you see it in a structure, go ahead and stick it in the middle because carbon likes to be at the center. Of structures, which means then the H is going to be on the outside and the N is going to be on the other side as well. All right. So next thing, we're going to connect these. They're going to float away, connect them with a single bond to begin with. And then we're going to make the outer atoms happy first by giving them enough electrons. We just said that the hydrogen here, okay, only needs 2 electrons. Right now, it has those 2, so it's already happy. It's content. So it's content with single bond, which are 2 electrons. So the nitrogen on the right, though, has 2. It needs 8 to be happy, so it needs 6 more. We're going to put those in as pairs of lone pairs of electrons. So now the nitrogen has 2, 4, 6, 8. And the hydrogen has 2, so they're both happy. If I look at my total electrons in here now, I have a total of 2, 4, 6, 8, 10. Those are my 10 valence electrons. Okay. This is not your Lewis structure, though, because even though the H and the N is happy, the carbon here is not happy because it only has 2 and 2, 4 electrons around it. So when you run into a situation where the central atom is electron deficient, after you've accounted for all the electrons, the central atom is electron deficient. After getting to your maximum number of electrons, then what we can do is we can move pairs of electrons to make double or triple bonds if we need to. Okay, so in this case, the carbon isn't happy. We can move a pair of electrons from here to make it now a bonding pair of electrons. So if I move it in and get rid of it and turn it into a bonding pair of electrons, the nitrogen is still good with 2, 4, 6, 8. The carbon now has 2, 4, 6. So it's happier than it was before, but it's still not completely happy. We need to move another pair of electrons in here to make a triple bond. And by doing that, now the carbon has 2, 4, 6, 8, so it's good. The nitrogen has 2, 4, 6, 8, it's good. I have a total of 10. Hydrogen's good. This is your legal structure for HCN. Okay, so you're going to run into, and you'll see several layers of drawing Lewis structures. This is one of them, where you have to introduce double or triple bonds to make that central atom happy with its octet.